I don't know actually. Don't leave the bar. Don't know.
Either one. Okay. Let's do it here.
All right, whenever you're ready.
Cool.
Make sure you change to Juniper on your on your form.
Hi everybody. So we are Juniper. We built a functional reactive programming language for the Arduino as a sort of substitute or transformation from Arduino C++. So the big problem is, I'm Lewis, by the way.
And I'm Caleb. And our sponsor is Sam Geyer.
So Arduino programming can be kind of weird because it's programmed in C++, but the Arduino is designed for commercial and casual use, and C++ is very low level, or at least comparatively low level to a lot of more modern languages. And it's not very intuitive for timing-based events unless you use some convoluted like polling machine mechanisms. And it often doesn't scale well for when you're adding new components. So say you built a new prototype, you're adding a new component to your Arduino. Sometimes that can involve a complete restructure of your code depending on how you did your last one, and so that can kind of make C++ a bit of a drag to deal with. So our solution was to build a functional reactive programming language called Juniper for it, custom fit for it, inspired by a bunch of other functional languages. Some features. So the reason why we did FRP was because it's actually designed for timing-based events, and the Arduino problem space is very much based on that. FRP is usually much more readable, especially if you know the language, but because it's more compact, effective code, it really helps its case. And it composes and scales well, so that means that when you add new components, it doesn't often just completely restructure the complexity of your program. Meanwhile, we built the language so that it's still very lightweight. It's more lightweight than a lot of other functional languages, and it still includes a lot of imperative features, which makes the transition to the language much more easy. And it includes an inline C++, which means that you can have more direct control over the hardware interaction. So after we designed the language and figured out how we want the syntax to go, we started building the compiler around it. We defined the abstract the structure of the abstract syntax tree for the language, which includes organization of data types, functions, how functions are stored, how any data that you code is stored. We defined the concrete syntax of the language, so anything from semicolons to lets, output, anything like that. And modules as source files. So in Python you have like these .py files and you do imports. In this language you have modules and you simply import modules. At compiler runtime, after the user has written his code, the code is his or her code. The code is lexed, so all the little concrete syntax is turned into tokens. That lexed code is then parsed, so all the data, all the variables, all the functions are then stored into the abstract syntax trees. We then type check that with static typing, which just helps keep the language lightweight into statically typed abstract syntax trees, which also makes the transition to C++ a little easier. Finally, we take those typed ASTs and we transpile them to C++. So we don't actually compile the language to binary. We actually just translate it to C++ that's already fit to be compiled to the Arduino.
Cool. So I thought I'd just go a little bit over how the language works. So Juniper supports a lot of features that you'll find in functional programming languages. We have support for things like pattern matching, lambdas, polymorphic functions, all of that good stuff. And we also have some imperative features as well, like for loops, mutable state. We also have these things called references, which are basically like pointers, but better and safer. So the main way that you structure programs in Juniper is using these concepts called signals. So basically, events propagate along these signals, And the key insight here is that at any point in time, a signal may have a value on it or it may not. So we can represent that with a maybe or an optional type. And that is literally the definition in the Juniper standard library of a signal. It's just a maybe type. And also we have this interesting feature called capacity variables. Basically this puts at compile time, it will put constrain the size of like an array, for instance, or any other data structure that you might make. So if you're familiar with things like dependent types, it's sort of like a dependent type system, but where the capacity is all known at compile time. So what we got right. So the compiler is finished, and I'm pleased to say that it runs on Windows and Linux. We haven't tested it yet on Mac, but it probably will run on Mac as well. We have a bunch of test programs that we built, and we're still testing some bigger projects. Like this one, for instance, is actually a GPS watch that I'm making. We also have a syntax plugin. So if you actually want to code it, you'll see the colors, the text will be highlighted, and that runs on Atom, which is a text editor from GitHub. And also documentation, both in the code, and we have automatically generated documentation for the libraries, which I will show in the demo, which is now. Okay. I'll just show the documentation stuff first. So here's an example of the documentation. There's a few modules in the standard library that I've documented so far. So for example, if you want to see how fold P works, you can just click that and it'll show up, and this is all pulled straight from the source code.
Are you in Atom right now?
No, this is the internet browser. So this will be linked from the website.
Oh, it's just a browser, okay, cool.
Yeah, but you'll go to Atom now. So this is demonstrating the syntax coloring plugin and also the Juniper language. You can zoom in a little bit. So if you're familiar with Arduino source code, basically this is all some setup stuff right here, determining what pins are being used and some other things. Here's an example of an algebraic data type. So basically what this program does is there's a ring of LEDs here. You push the button, the LEDs change to green, and then blue, and then back to red, and then so forth. You just push the button and the LEDs change color. So it's a pretty simple program. And we represent that with an algebraic data type. We have some other functions here. So transition mode, if you're in red, go to green. If you're green, go to blue. A function which converts the mode to a color. So these case statements are actually examples of some pattern matching features. Set ring color, which simply sets, actually displays the NeoPixel color. Here's some more setup code. And this is the main core part of the this Juniper program. So basically what happens is we take an input signal from the button, which is this line right here. We debounce it using this line, and we capture the falling edge of the button, and that produces a new signal. Then we pass that signal to a fold P function. This fold P stands for fold over the past. Basically what it does is it will mutate this mode ref into the new state. You can see it calls a transition mode function from before. And then finally it passes that into a sync, which will then set the color of the ring. Okay, so I'm going to go to the command line.
If you pass it around.
Oh, yeah, I'll pass this around a little bit after I'm done with the demo. And we'll compile the program and wait for it to compile. Okay, and it generated some C++ code here. So you can see that it's quite lengthy. And I'll upload it to the Arduino now.
Can you link it to pretty much any library?
So what do you mean?
Well, if somebody had a different library that was C++, can you link?
Yeah, so you have to write basically a wraparound library. So I did that for the NeoPixel stuff, and it's really easy to do because you can drop straight to inline C. Going back to the demo, I will upload it to the Arduino. It's going to give me an error because I didn't push the reset button. Okay, here we go. Okay, and it's uploading now. And we got red. And we can change it by pushing the button.
Still party mode on there?
Oh no. On my GPS watch, I have this party mode feature which flashes a bunch of different colors. It's pretty cool. You can take a look at that later. Yeah. Okay. Back to the presentation.
So, some things we need some work on. We mentioned what we got right about it, some challenges for what we haven't done yet, or that we kind of fell short on. One thing, the parser we used needs to be replaced. We kind of built the parser off of F# Lex and Yak. The problem is that there's been like some accumulating problems, and as we've bug fixed, we've been accruing a lot of technical debt, and we kind of want to move to a different system, which is much cleaner, wouldn't involve as much of that. Second thing, performance issues. You saw there was a lot of C++ generated. It's actually funny, in a lot of our test programs, our language actually was much shorter than, say, if you were to write it in C++ comparatively, and is actually more readable in a lot of ways. But the generated C++ can still be shorter, and we can still improve on that. Next thing, it's actually, in a lot of ways, especially if you know functional programming, is more readable than Arduino C++. The big problem is that it's still less readable than other functional languages, and we would probably want to work more on making it have like a readability that's similar to a lot of other functional languages. Things like a type inference system, for example, would help a lot with that. And lastly, we have not yet finished the coding tutorial. That's actually something we're going to be working on for the next week or two. We have the documentation inline and out of our actual compiler, and we have instructions on how to compile the compiler, how to write code for it, and how to run the compiler, but we haven't actually built a tutorial for the language itself yet. But we're working on that. So because the entire project is open source, the compiler, the Atom plugin, the Juniper standard library that we built around the language, anybody can really pick it up and build on it however they want. So some ideas we have for how it can be built on in the future include building a complete type inference system. There is some like little type inference here and there in our type checker, but not to a complete extent, and that would really make the code cleanup look a lot better in a lot of ways. So we didn't have to have those little carrots and have those types as much. Code optimization, as I mentioned, really making for cleaner C++, making sure that just the language runs faster, making the parser actually run a little, the actual compiler run a little faster, expanding the standard library. So we built like a lot of features for the Juniper standard library, but there's always more of the C++ standard library that can kind of be transferred over in terms of features. Improving on language semantics. If someone proposes a redesign of how the language should look so that it looks much more readable and a lot more easy to write, then by all means. And also just any other expanded features that people might want to implement into this project. It's kind of open-ended.
Cool. We'd like to thank Sam Geyer, who is our sponsor. He's been a pretty good resource for bouncing ideas off of and giving general advice, and also to Chris for having the class. And here's some references, the YouTube videos that we've watched, and also Sam actually gave a presentation last year which kind of kicked off this project, which you can watch on YouTube if you want. I think Chris actually recorded it. Any questions? Yeah.
Do you have some sort of issue when embedded C++ conflicts with generation C++?
What was that? Oh, conflicts.
Variable names, scope and
So the inline C++ is placed inside of a immediately invoked lambda. So it's not actually going to you can't throw in a bunch of like variables into the scope of the function and have it collide. But also that means you can also like use the same variables names and stuff. Like we don't mangle the names or anything like that, which is really nice if you're writing inline C++.
What do you mean with the error message?
We can actually demo an error message quick.
The type checker?
Yeah.
Yeah, they have.
So like, if I say this button signal is secretly a uint32, which it's not, let's recompile that. Hopefully it'll catch it. Yeah, okay, so got an error message. So basically, it'll give you the line number and the position number, and it'll point to where the error is occurring. So in this case, conflicting type error.
In the abstract syntax tree, we actually include, because that's how a lot of compilers do it, positions for all the data in the actual code. So reporting error messages by the line and column actually helps a ton. I mean, it's actually made a lot easier.
All right, guys, I think this is really cool. I would love to see it online where a community can maybe try to get built around it. It would be very
Yeah.
cool. Very
Yeah.
cool. This is, as far as I know, this is the first functional language for going straight to Arduino, correct?
There is a competitor, but it looks like the project is dead now because they haven't worked on it for a year, so we're good, I think.
All right.
Monopoly!
Anybody have any other questions? All right, very good job, guys.
Actually,
What do you guys want to add to the standard library?
it's just basically all the typical things you would find in a functional programming language. There's a lot of stuff that's not in there yet. So if you want to help write it, that'd be cool.